Hi, in our previous videos, we have looked at how we use a calculator to find the value of certain trigonometric ratios. But for certain angles, we do not need to use a calculator. These angles are known as special angles. Special angles include 0, 30, 45, 60, and 90 degrees. The sine, cos, and tan ratios, as well as their reciprocals, have specific values when it comes to these angles. In this video, I'd like to look at how we find the values for special angles. Let's put our table in here, and we can include sine, cos, and tan. We use right angle triangles and the Cartesian plane to prove the values of these special angles. Let's make some space and start by drawing a right angle triangle. Let's mark down our right angle, and we can write in 90 degrees in here. Let's draw an angle at the top of the triangle and again at the bottom. Our special angles are 0, 30, 45, 60, and 90 degrees. We cannot draw an angle of 0 degrees in a triangle. So let's move on to 30 degrees. Let's say that the angle at the top of the triangle is 30 degrees. Now we need to find the size of the angle at the bottom of the triangle. We know that the sum of the interior angles of a triangle are equal to 180 degrees. So let's find the size of the third angle. And we can say 180 minus our 90 degrees, which leaves us with 90, minus the 30 degrees, which leaves us with 60. So we can put 60 degrees in over here. Before we look at the different trigonometric ratios, we need the lengths of each side of the triangle. Let's say the length of the side at the bottom is 1 unit long, and let's say the length of the hypotenuse is 2 units long. Now we can use Pythagoras to find the length of the third side. So we can say 2 squared minus the length of our other known side, 1 squared, all under a square root. 2 squared is 4, and 1 squared is simply 1. 4 minus 1 gives us an answer of 3 under a square root. So let's write this on our diagram as well. Now, we have not randomly made up the values of the lengths of each side of the triangle. These specific lengths will help us to find the values of the trigonometric ratios with 30 and 60 degree angles. So please make sure that you can draw this triangle and use the length of each side. Now we can look at our trigonometric ratios. From SOHCAHTOA, we know that sine theta is equal to the opposite over the hypotenuse. Cos theta is equal to the adjacent over the hypotenuse. And tan theta is equal to the opposite over the adjacent side. From our previous videos, we know that the hypotenuse of a triangle is directly opposite the 90 degree angle. So let's put an H on our diagram for hypotenuse. We also know that the position of the opposite and adjacent sides will depend on the angle we are focusing on. Let's start with our 30 degree angle at the top of the triangle. From here, we can see that this is our opposite side, so we can mark it with an O. And this is our adjacent side, so we can mark with an A. In this case, we can see the length of the hypotenuse is 2 units, the opposite side is 1 unit, and the adjacent side has a length of square root 3. With these, we can now find the values of the trigonometric ratios for a 30 degree angle. So for sine, we can say sine, our angle, 30 degrees, is equal to the length of the opposite side, 1, over the hypotenuse, which is 2. Let's make a note of this in our table. Now we can look at cos. So we say cos 30 degrees is equal to the length of the adjacent, square root 3, over the length of the hypotenuse, which is 2. Let's put this into our table as well. Finally, let's look at our tan ratio. So we say tan 30 degrees is equal to the length of the opposite side, which is 1, over the length of the adjacent side, which is square root 3. And we can put this value into our table as well. Let's tidy this up. And now we can look at our 60-degree angle. Regardless of the angle we are focusing on, the hypotenuse of the triangle is always directly across from the 90-degree angle. So let's put our H back in over here. From the 60-degree angle, this is now our opposite side, and this is our adjacent side. The hypotenuse is still 2 units long, but now the opposite side has a length of square root 3 units, and the adjacent side has a length of 1 unit. With these, let's find the values of our trigonometric ratios for a 60-degree angle. So now we can say sine our angle, 60 degrees, is equal to the length of the opposite side, root 3, over the hypotenuse, which is 2. Let's make a note of this in our table. Now we can look at cos. So we say cos 60 degrees is equal to the length of the adjacent side, which is 1, over the hypotenuse, which is 2. Let's put this into our table as well. Finally, we can look at our tan ratio. So we say tan 60 degrees is equal to the length of the opposite side, root 3, over the adjacent side, which is 1, and root 3 over 1 is simply root 3. And we can put this into our table as well. In this triangle, we have a 90-degree angle, but we run into some problems when trying to find the opposite and adjacent sides. The hypotenuse is always the side directly opposite the 90-degree angle, but if we are focusing on this angle, then the hypotenuse would be the opposite side as well, and then we have 2 adjacent sides. So we cannot use any triangle to prove the values of trigonometric ratios for 90-degree angles. So let's tidy this up, and now we can look at a 45-degree angle. Let's draw in another right angle triangle, mark down our right angle, and put 90 degrees in over here. Let's put an angle at the top of the triangle and another at the bottom. I want to look at a 45-degree angle. So let's put 45 degrees down here. Now we need to find the size of the other angle. So we can say 180 degrees less 90 degrees less our 45 degrees, which leaves us with 45. So this is a 45-degree angle as well. Let's say that this side of the triangle is 1 unit long. We know from geometry that if we have a triangle with 2 equal angles, we are working with an isosceles triangle, which has equal sides as well. This means that this side is also 1 unit long. Now we have the length of 2 sides. We can use Pythagoras to find the length of the hypotenuse. So we can say the length of one side, which is 1, squared, plus the length of the other side, also 1, squared, all under a square root. 1 squared is simply 1, so now we have 1 plus 1, which leaves us with 2 under a square root. Let's put square root 2 on our diagram as well. Now we can make some space and write down our sine, cos, and tan ratios. We know the hypotenuse is directly across from the 90-degree angle. So let's put an H on our diagram over here for hypotenuse. We have 2 45-degree angles, so you can use either one to determine the opposite and adjacent sides. The lengths of these sides are both 1 unit long, so it doesn't matter which angle you use. We're going to focus on the angle at the bottom of the triangle, which means that this is now our opposite side, and this is the adjacent side. We now have an hypotenuse, which is root 2 units long, an opposite side, which is 1 unit long, and an adjacent side, which is also 1 unit long. With these, we can now find the values of the trigonometric ratios for a 45-degree angle. So let's start with sine, and we can say sine 45 degrees is equal to the opposite side, 1, of the hypotenuse, which is square root 2. Let's make a note of this in our table. Now we can look at cos. So we say cos 45 degrees is equal to the adjacent side, 1, of the hypotenuse, root 2. Let's make a note of this as well. Finally, let's look at our tan ratio. So we say tan 45 degrees is equal to the length of the opposite side, 1, over the adjacent side, which is also 1. 1 over 1 leaves us with 1. Let's put this into our table as well. Now we have values for the trigonometric ratios for 30, 45, and 60-degree angles, but we still need to determine the values for 0 and 90-degree angles. We cannot use triangles to find the trigonometric ratios for 0 and 90-degree angles, but we can use the Cartesian plane. Let's make some space. Now we need to consider angles of 0 degrees and 90 degrees. So we only need to consider the first quadrant of the Cartesian plane. So let's draw in our axes. The x-axis runs horizontally and the y-axis runs vertically. We know from our videos on the Cartesian plane that we draw angles from the x-axis at 0 degrees and reach 90 degrees when our angle touches the y-axis. Here we are only working with quadrant 1, and in this quadrant, both our x and y coordinates are positive. We know that when working with the Cartesian plane, sine theta is equal to y over r, cos theta is equal to x over r, and tan theta is equal to y over x. The origin is the point where the x and y axes cross. So let's mark this with a black dot. And we can draw our terminal arm from the origin to anywhere on the Cartesian plane. We have learned that to draw an angle on the plane, we start on the x-axis to the right of the origin and move in an anti-clockwise direction, depending on the angle we need to draw. So if we want to draw an angle of 0 degrees, all we do is draw our terminal arm along the x-axis like this. Let's draw a point on the axis at the end of the terminal arm and call it P. Let's say the length of the terminal arm is 1 unit long. Now the x-coordinate of point P is the distance between P and the origin along the x-axis. The point is 1 unit from the origin, so the x-coordinate of point P is 1. The value of the y-coordinate is the distance of the point from the x-axis. Point P is on the x-axis, so our y-coordinate is 0. Let's make a note of our coordinates, 1 and 0. Now we can see that x is equal to 1, y is equal to 0, and r takes on the length of the terminal arm, which in this case is 1. Now we have values for x, y, and r, so we can find our trigonometric ratios for an angle of 0 degrees. And we say sine 0 degrees is equal to the value of y, 0, over r, which is 1. Any fraction with a numerator of 0 is simply 0. And we can put this in our table. Now we can look at cos. So we say cos 0 degrees is equal to the value of x, which is 1, over r, which is also 1. This leaves us with 1. Let's put this value into our table. Finally, let's look at tan. So we say tan 0 degrees is equal to the value of y, which is 0, over x, which is 1. And 0 over 1 is simply 0. And we can put this into our table as well. Finally, we can look at the trigonometric values for a 90-degree angle. So let's make some space. We start drawing a 90-degree angle by drawing our terminal arm along the y-axis above the origin. So we can draw it in over here. Again, let's put in a point at the end of the arm and call it P. our terminal arm is 1 unit long. Our point is on the y-axis. So in this case, our x-coordinate will be 0. And our point is 1 unit away from the origin along the y-axis. So our y-coordinate will be 1. Let's make a note of this. And we can say 0, 1. Now we can rewrite our sine, cos, and tan ratios for the Cartesian plane. Our x-coordinate is 0. So let's make a note of this up here. And our y-coordinate is 1. So let's make a note as well. R takes on the length of the terminal arm, which is still 1. So R is equal to 1. Now that we have our x, y, and r values, we can finally find the values of the trigonometric ratios for a 90-degree angle. So for sine, we can say sine 90 degrees is equal to the value of y, which is 1, over r, which is also 1. So we get a total of 1. Let's put this into our table. Now we can look at cos. So we say cos 90 degrees is equal to the value of x, which is 0, over r, which is 1. 0 over 1 leaves us with 0. Let's put this into our table as well. Finally, we can look at our tan ratio. So we say tan 90 degrees is equal to the value of y, which is 1, over the value of x, which is 0. Now remember that any fraction with a denominator of 0 is undefined. So tan 90 degrees is undefined, and we can put this into our table as well. When working with special angles, you will also need to use the reciprocal ratios. To find the value of a reciprocal, we simply flip the value of the original ratio around. Please make sure that you learn all the ratios for special angles, their reciprocals, and how to draw their respective triangles and angles on the Cartesian plane. You will need to know this in your final examination.